We're going to take advantage of that moisture we talked about last week to discuss how clouds and precipitation form and how weather radar can look and see literally the precipitation within a cloud. So it's not as simple as you might think. So water vapor is invisible. So there's always water vapor in the air. So when you look outside and can see 20 miles or have great visibility, there's still water vapor in the air. Now, clouds we can see, and they're contained water, liquid water normally, or frozen ice crystals. So they're a product from that water vapor that's always there. So there's several things, however, they don't form easily, which is kind of strange. They form, we need cloud condensation nuclei. So we're going to talk about what they are. And also, on the average, about 67% of the Earth is cloudy. So that's a lot of the Earth. So here you can actually see they use satellite to determine clouds. And notice the aerial coverage with time is greater than 50% down here in the tropics and over the oceans. However, the deserts, like the Sahara and all, much significantly less. But this was a 3-year average, so they had a pretty good average of how much clouds were around. All right. In order to have a cloud form, you have to have tiny droplets of water form first. So we're going to do a comparison. A raindrop relative to this size of a cloud droplet. Notice how much bigger the rain droplet is. The cloud droplets are really tiny. So if you think about that, it causes some problems as far as how these cloud droplets form. They form obviously when evaporation and condensation are equal because you need saturation, and that's what happens. Relative humidity of 100%. However, there's a curvature effect to these cloud droplets. In other words, everything we've based on relative humidity up till now has been on a flat surface. In other words, flat lake, flat ocean. Now, all of a sudden, we have a very significantly curved surface. Those very, very tiny droplets have a very sharp curve to them. That means that the relative humidity, in order for saturation to occur, must be significantly higher than 100%. Literally, it means they've got to be up around 300 or 400%. So in that case, we would never have clouds. So something else has to happen. That something else is called the salute effect. So we're going to go through these two effects here and determine how clouds actually form. And you can see here, when you look at this, how tiny these raindrops are. And because of that strong curvature, it allows a lot of that water vapor that starts to condense to evaporate back out. And literally, the evaporation wins. And with that, here's a graph showing literally how much saturation you would need for droplet size. So once it starts getting a little bit of size to it, then it goes back down to 100% relative humidity. But these very, very tiny droplets, you need a heck of a lot of relative humidity, literally 300%, like it says here. However, the salute effect offsets that. What happens is there are cloud condensation nuclei, and they reduce saturation to around 100% or less in these very tiny water droplets. They literally dissolve in that droplet. So some things that might dissolve in that are salt, some kinds of dirt, different things will do that. And what they do is manage to hold those molecules together of water in that little droplet so that instead of going back out and evaporating into water vapor, they stay a liquid. So now that we have these tiny cloud droplets in clouds, we can see the clouds in the sky. And the kind of aerosol that you might have in those clouds, if you were in the Midwest, a lot of it is dirt, literally, a type of dirt. Around cities, there may be aerosols in the air put out by industries. Around the oceans, it's almost all salt. Interestingly, within clouds, the water droplets don't freeze. Literally, they have to get well below freezing before they will actually freeze instantaneously. So now we have another kind of dirt particles, ice crystal kind of thing that helps to promote freezing. These are freezing nuclei, ice-forming nuclei. There aren't as many of them as condensation nuclei. But what they'll do is they'll cause water droplets to start freezing at about 16 degrees Fahrenheit. So in the cloud, when the temperature gets cold enough and we have these ice-forming nuclei, water droplets begin to freeze and change from liquid to ice crystals. So we have a range here when water temperatures, literally in the cloud, are well below freezing or super cool. If you go down to minus 38 degrees Fahrenheit or minus 39 degrees Celsius, it's called the Schaefer point. That is where everything freezes instantly. You don't need no condensation nuclei or no ice forming nuclei. Everything will freeze there instantaneously. But that is hard to get to, so most happens otherwise. Now, we have these clouds, they're floating up in the sky, right? Nothing's coming down out of them. And then it begins to rain or snow. The only way that is going to get down to Earth is if it overcomes the air resistance. Remember, air has friction involved with it. We discussed that a little bit and how different humidities, temperatures change the density of the air. The more dense the air, the more friction in the air. So these water droplets that get big enough and start falling actually have that friction impacting them. And that causes them to reach what we call terminal velocity. Gravity is what's pulling them down, friction is pulling them back up. Both of them are constant, so they don't change. And eventually they equal each other, and that will be the speed that raindrops or snowflakes fall. So how do these raindrops fall? How do we get these droplets in clouds big enough to come down to the ground? Well, there's two processes. One is a collision coalescence, which happens in warm clouds. Temperatures got to be above freezing for that to happen. Or we have what we call the Bergeron-Findyson process, which actually most clouds have ice in them. That is the predominant method of how snow, rain form. But we're going to look at the nice warm one first. So what happens is you get a little bit larger particle in the atmosphere, a little bit bigger raindrop or cloud droplet, and it starts to fall a little bit, and it hits another little tiny cloud droplet, absorbs it, hits another one, absorbs it, until you get a droplet big enough to fall on its own and actually be a raindrop. That's how collision coalescence works. However, ice crystals can take over these literal and cold clouds. Ice crystals are going to grow faster than the raindrops. And why is that? Well, That's called the Bergeron-Findeisen effect. And what happens with it is that we learned last time that right around the freezing point, when there's ice versus water, saturation vapor pressure is greater over water because it's in a different state than over ice. Because of that, water vapor is going to go from the water droplets to the ice, and it's going to cause the ice to increase. As the ice is increasing, there'll be more and more ice crystals and less of the water droplets, till eventually the whole cloud is ice. And these ice crystals, because they keep growing, get heavy enough that they begin to fall out of the cloud. As they come down, warm, melt into rain, now they're going to interact with other rain droplets and get even bigger and come on down to the ground as rain, maybe. Or if it stayed all snow all the way down, come down to the ground as snow. But that's how the process works. Here you can see virga. Sometimes underneath these clouds, the precipitation falls into very, very dry air. This happens a lot out west, uh, especially if it's over the deserts and stuff. You can see these great thunderstorms develop. You can see the rain coming down out of them. Underneath it, all that rain's evaporating, and it's a virga. So rain, very small diameter, 0.5 to 6 millimeter. Usually not a teardrop. They're usually fattened spheres. And then drizzle is much tinier. Originally locates on stratus clouds, usually pretty low, and definitely only through collision coalescence. There are two types of precipitation. Here's snow. Interesting, snow has a lot of different shapes. I want you to look at something. If I'm forecasting snowfall for your house, and I have this shape, or this one, or even this, and then compare it to a dendrite. Look how much bigger the dendrite is. So if I'm going to have snow at your house, I need to determine which shape that snow is going to be. That will determine how much snowfall you get. If I had dendrites, I can add literally 10 to 20% more snowfall than if I have one of these other types of snow. So when you're forecasting snow at your house, one of the things the forecaster is going to do is determine what type of snow is going to fall. Will it be snow pellets? Will it be a dendrite? All right, if we know that warm air rises over top the cold air, when that happens, and I kind of showed you some of this the other week here in a storm we had where we had a lot of ice around and snow changed to rain. Well, what happens is you get some strong pushes of warm air in. If you have a lot of warm air in, the clouds above it form snow, falls into that warm air, it melts, and we get rain at the ground. Almost most of precipitation in the United States during the summertime is rain, obviously. And in the wintertime, a lot of it still is some kind of rain. Now, that warm air, big layer of warm air, but right near the ground, we have a layer of pretty cold air. What happens is all that rain coming down hits this cold air and it freezes instantly. That's freezing rain. However, if that amount of cold air is a little thicker and the amount of warm air is a little thinner, you wind up getting these raindrops coming through here. They're not really very warm raindrops. They're quite cold. They may even be super cold. They instantly freeze into sleet. And finally, where you don't have that warm layer, or even just a tiny little bit of it, it might not melt all of it, you wind up with the snow. So one of the things meteorologists always look for is how these warm layers aloft take shape, how thick they are. These can make a big difference on where the snow is going to fall, where the rain is going to be, or where sleet is going to be. Hail. All right. In a thunderstorm, you have tremendous updrafts, sometimes over 100 mile an hour up. What happens is, in that updraft, rain is being pulled upwards, it's getting to freeze some, and it's getting spit out of the updraft next to it. It starts coming back down, and then it manages just to pick up some liquid water, gets caught in the updraft again, and just repeats itself until it gets too big to even be held up by the updraft. The bigger, the stronger the updraft, the bigger the hail can be. And here is that freezing rain, that sounding I was showing you, where the temperature is just above freezing for a short layer here, enough to melt the snow. All right, radar is a wonderful way of detecting rainfall, clouds, different things. It actually can detect bugs sometimes and birds taking off. We have to differentiate from those to understand what they are. Radar operates in two modes: reflectivity mode. That's where it detects what precipitation is falling. In velocity mode, it detects how those particles are moving horizontally, not vertically, horizontally. So the radar rotates around in its cell very quickly. It will, and the antenna, instead of just staying at one angle, actually tilts upward with time till it reaches 19.5 degrees. Then it comes back down and starts the process again at 0.5 degrees. And the interesting thing is about radars, they listen 90% of the time. So they'll send a pulse out, and 90% of the time, then they're listening for that pulse to return. When it does, they know how far, how long it took that pulse to get there, and they can determine if the frequency has shifted. Both of those things are important. One determines distance, one determines the direction of motion. And here you can see the big antenna inside the dome. And here's the Doppler shift. You can see how the frequency changes, whether it's coming towards you. And these are, interestingly, we're looking at literally perpendicular. So we cannot detect velocity. There are zero where the velocity shows up at zero. That's where it's moving exactly parallel to the radar. But with that wonderful velocity and using it reflectivity, now that we have those, we can look at an area here. You can see the dark red is very heavy, intense precipitation. Here we have velocity. One's going this way, one's this way. You'll notice the closer together these two very strong velocities are, that's where a tornado may form. And now we add in dual pole. We're going to talk a little bit about dual pole here in a minute, but with it, you can get things like debris signature. Literally, we can distinguish debris from precipitation. And with it also, we can use it on severe weather and hurricanes. Like this is a hurricane. It's coming ashore near Morehead City, North Carolina. You can see the eye right here, very strong band of rain there. Tremendous winds right here in this area. There's another type of radar called phased array. You'll see it on warships. However, there's actually one put together down in Norman, Oklahoma, that they use for testing. The cost of these is almost $1 billion per radar. So they're not cheap. And because they don't make a huge difference in our forecast, government still doesn't want to buy any right now. That's fine. However, if you use one, what it does is scan the entire atmosphere. Where I told you the other tilted, this does not. This literally looks at the whole atmosphere instantaneously. So you can literally watch tornadoes develop very quickly and get a warning out maybe 5 to 10 minutes quicker than you would otherwise. One way of measuring rainfall is using a tipping bucket. Uh, all it does is literally it sits there, it gets enough rain in it, it weighs to a certain point, and it'll tip over and pull that rain right out. Every time it clicks like that, it's 1/100th of an inch of rainfall. So the faster the clicks, the heavier the rainfall. Snow depth was measured on a snowboard. Believe it or not, we put boards out, measure the snow every so often to see how high it got on that board, clean the board off, and start the same process. That's how estimates of snowfall are arrived at. Radar can determine the amount of precipitation falling, as can global satellites. Some of them have that ability as well with radars in them. And here you can see the estimated rainfall that occurred at New Orleans during Hurricane Barry. Notice some really, really tremendous rainfalls up along here in these these valleys out from the city. All right, the last part we're going to talk about is different clouds. I'm going to have you this week discuss the clouds around your area. There are three basic clouds: a cirrus cloud, cirriform cloud, high cloud that is, stratiform or layers, cumulus or bumpy. Warm clouds have temperatures above freezing, cold clouds, temperatures below freezing. So high clouds, cirrus clouds, there's cirrostratus, which is a layer of cirrus, cirrocumulus, which is bumpy. So you're basically taking the three categories and combine them right here. The same will occur in alto clouds. Altos are mid-level clouds. So you have altostratus and altocumulus. They can have some mixture of ice and liquid in them. Finally, as we get down, we have stratocumulus or stratus clouds, or even nimbostratus, where it's precipitation occurred. Cumulus clouds are just puffy clouds, and when they become bigger, like cumulus congestus, is like a towering cumulus cloud, and finally you get a cumulonimbus or a thunderstorm out of it. Here you can look on satellite. Notice all the bubbles in the clouds here, how they just kind of pop up there. But they're more uniform out here. So these are cumulus clouds in this area right here. We call about cloud streaks. When you're living in West Virginia, Ohio, around the Great Lakes, especially in the fall and early half of winter, you get lake effect snow. You can literally watch the wind blowing over the lakes. It takes a little bit of time for it to get moist. Once it does, it starts developing clouds, and then those clouds come into land and dump down precipitation. Sometimes you can get a line of clouds coming off of one lake into another lake, into another lake. Literally can watch this go from 3 different lakes, so it has a chance to get even more moisture and dump heavier precipitation. There's an unusual cloud called altocumulus lenticular. It occurs on mountain ranges. What happens is air comes down the mountain, and if it's stable, it actually still causes little wave patterns. And when it does that, it will cause clouds to form when the wave going up. So you wind up with cloud streets on the opposite side of the mountain. On the west side, for example, where the wind come into and causes a lot of updraft, you get more solid clouds. On the eastern side, like the Appalachians, you may get these lines of clouds. If you're flying an aircraft at a low level, you're going to run into these clouds and you're going to bounce around a lot. That's where most of the turbulence is. Many aircraft try to avoid these areas. Fog is just cloud on the ground. It literally develops when temperatures and the air becomes saturated. We know that cold air sinks, so saturation is going to tend to occur in the lowest layers. Here, for example, you're looking at the Grand Canyon. Notice the solid layer of fog in the Grand Canyon. Up on top, it's a beautiful day. This happens in river valleys. It can happen in mountain valleys with no water at the bottom. The air will flow down the mountain in West Virginia, for example, cool, reaches saturation, fog begins to form on the bottom. And if it keeps developing upwards, maybe it gets up almost to the top of the mountain. You can also get fog coming off of water. I'll give you an example of this from the Gulf of Mexico. When I was at Florida State, we had air that came in off the Gulf of Mexico one day. The Gulf of Mexico was relatively warm uh, compared to the land. The land was a little bit cooler at that time. So as that air came in, had lots of moisture in it, it cooled once it hit the land and began to develop fog. And the fog kept getting thicker. I was at a football game, and literally by halftime, you couldn't see across the field. And all of this was advection fog coming in from the Gulf of Mexico. We can get fog from upslopes on mountains sometimes as well. Well, I think that's about it. I hope you got something out of this. Let me know if you have any questions.